Hi guys, welcome back to 7 Steps to a 7 in Olympiad Geometry. In this video, we're going to be exploring trigonometry and lengths. We're going to start off by reviewing some of our basic trig facts that you should probably know, and then we're going to be looking at Ceva's and Menelaus' theorem. And we're especially going to look at the law of sines, because the law of sines is probably the most important trig theorem inside Math Olympiads. So without further ado, let's get into it. So obviously the first theorem we're going to be discussing is the law of sines. But before we do anything, we have to let ABC be a triangle. We're always going to be using this notation. So ABC is a triangle, and we're going to let, for simplicity, BC equals A, CA equals B, and BA equals C. All right, so now with that out of the way, let's go ahead and state the law of sines that you probably already know. So the law of sines states that if you have a circumcircle ABC and the radius is r, then this means that the value a over the sine of angle A, so the BC over here over the sine of angle BAC over here, is equal to B over sine angle B is equal to C over sine angle C. And all these lengths are equal to 2r. And if you want to know how to prove this, then you want to prove that A equals 2r sine angle A. And with this, you can construct like a right triangle like this. And then we know that this is equal to angle A, and this is 2r here. So if we let this point be x, then bx equals 2r, and angle BXC is equal to angle BAC by cyclic quadrilaterals, which means that because this is a right angle here, if we construct it as such, this means that BC is equal to 2r sine angle A. All right, so that's the law of sines. But how do we relate the sides of the triangle to the cosines of the angle? Well, here's how. It turns out that if we look at specifically angle A, we have that c squared plus b squared minus 2bc cosine angle A is equal to a squared. So this is the law of sines, and this is the law of cosines, which you probably already know from computational math. So you have this law of sines and law of cosines, and these allow you to solve for the sine of the angle and the cosine of the angle. Or if we know the cosine of the angle, we can solve for the other sides. And here are some applications of the theorem, some basic ones or corollaries. So if cosine is equal to 0, then cosine equals 0. That implies that angle A equals 90. And c squared plus b squared equals a squared. And this is exactly the Pythagorean theorem. So that's one way to apply the law of cosines. And for the law of sines, we don't really use this 2r part, but we highly make use of this. A over sine angle A equals B over sine angle B equals C over sine angle C is equal. And because these guys are equal, we can solve for all of the sines in terms of other lengths. And we're going to be using this a lot inside our Olympiad problems. All right, so here's an example of how we can use the law of sines. Our first example, as we see here, is actually a very important lemma inside Olympiad geometry. So if ABC is a triangle and T is a point on side BC, then TB over TC equals AB over AC times the ratio of these two sides. All right, so how do we get started on this problem? Well, you can probably guess the first step of any Olympiad geometry problem. And before I do it, I highly recommend to do it yourself. All right, so let me perform this first step, which is, of course, drawing the diagram. So we have ABC here. That's our triangle. And we have a point T on the side. So here's our point T. We want to prove that these ratios are equal to each other. So now what do? Well, we want to somehow involve sine angle TAB and TAC in some way. And so we want to use the law of sines in order to involve these signs. So the only triangle that really uses this angle TAB here is, well, the triangle TAB, because otherwise we can't really introduce this angle here. So let's try using the law of sines on TAB. So when we do this, we end up getting that TB over sine angle TAB is equal to AB over sine angle ATB is equal to AT over sine angle ABT. All right, and we can do something similar with TC and ATC. So we have TC over sine angle TAC is equal to AC over sine angle ATC, and this is equal to AT over sine angle ATT. All right, so now we've used the law of sines, but now we need to do something with these two equations. Because I mean, we have a sign here, one of our signs goes here, and the other sign is over here. So we want to do something with these two equations such that we can get both of the signs in the equation. And we want the sine angle TAB, this one here, to be on the numerator of our result, and the sine angle TAC to be on the denominator, because that's the only way we can get our result. So if we try multiplying these two equations, then we get both sine and sine on the denominator. And adding the equations won't really do anything because we want to combine these factors. So let's try dividing the equations. And since we want the sine angle TAC to be on the denominator, and it's already on the denominator here, let's divide this equation here by this equation here. So 1 divided by 2, then 1 divided by 2 gives that we have TC over TB times, now we have the sine angle TAB over sine angle TAC. And now with this, we have that we want to figure out which of these expressions here we want to divide. For example, we could divide this one by this one, or this one by this one, or this one by this one, or this one by this one. And since we have an AB and AC over here, it makes sense to divide these two. So when we divide them, we get AC over AB times, then we have sine angle ATB on the numerator and sine angle ATC on the denominator. All right, so what can we do now? If we try rearranging it into our desired form, then we end up getting that we can move the TB over TC over here because we want to make it separate from these signs, and the AB over AC on this side because we want to combine it with the signs. And when we do that, we end up getting AB over AC times sine angle TAB over sine angle TAC. And that's equal to TB over TC times this remainder sign, ATB over ATC. All right, so we have this remainder term here, and the goal is we want to show that this is equal to 1. And the only way this can be equal to 1 is if their signs are equal. So sine angle ATB equals sine angle ATC. And now we haven't used the fact that t lies on BC yet. Otherwise, we could have just done all of these steps on our own. But as it turns out, we actually have that because t lies on BC, these two angles add to 180 degrees. And because they add to 180 degrees, this means that the two sides of the two angles are equal. So that means that this term cancels out, and what is left is this final expression here, which we call the ratio lemma. Now, you shouldn't memorize this ratio lemma here. Even though it's very important, you should not memorize it. Even I haven't memorized it properly, but I remember the proof. And the proof is the most important part of this lemma because it shows you how you can do manipulations with the law of sines. Because usually you use the law of sines to introduce some angles here, like this one or this one. And from this law of sines, you can end up doing a bunch of manipulations to get the desired form. And the fact that t lies on BC leads me to a second point about the law of sines, where in law of sines chases, where you have to chase lengths, it's always a good idea to angle chase as much as possible. Because by angle chasing as much as we can, we determined that these two angles add up to 180 degrees, which made this term here entirely cancel out. All right. And everything until sine ATB equals ATC holds until the last step, which kind of motivates the solution. And here's a small remark. If TAB equals TAC, these two angles here, then this should reduce to a theorem that you probably already know from Olympiad, from normal geometry. Now, sometimes we want to figure out how the sines of certain angles relate to each other. Because even though the law of sines solves problems on its own by repeated applications and manipulations, sometimes we get stuck and we don't know how to perform operations with sine. For example, how do we find sine of alpha plus beta for these angles alpha and beta? Or if we don't really know alpha and beta, how can we multiply their sines? Well, luckily for us, we have the angle addition and subtraction formulas for sine and cosine, and the other tool we will use directly follows from this. So what are these addition and subtraction formulas? Well, here they are. So sine of alpha plus beta is equal to sine of alpha cosine beta plus cosine alpha sine beta. And cosine of alpha plus beta is equal to cosine alpha cosine beta minus sine alpha sine beta. And you probably already know this from your pre-calc class or something like that, but if you don't, be sure to memorize these. As far as I know, there's no simple proof of these beyond other than using complex numbers. And the subtraction formulas follow immediately from this because sine of alpha minus beta is equal to sine of alpha plus negative beta. And that's equal to sine alpha cosine negative beta, which is cosine beta, minus cosine alpha sine beta, because sine negative beta equals negative sine beta. And we similarly get that cosine of alpha plus beta is equal to alpha minus beta is equal to cosine alpha cosine beta plus sine alpha sine beta. And these directly follow from these. Now, from these addition formulas, we can end up getting some very useful corollaries. For example, if you take alpha equals beta in this formula here, then we get sine of 2 alpha equals 2 sine alpha cosine alpha. This one is very, very useful in reductions when we have twice an angle. And similarly, cosine 2 alpha is equal to, when we plug it in here, cosine squared alpha minus sine squared alpha. And this has other forms such as 2 cosine squared alpha minus 1 and 1 minus 2 sine squared alpha by using the fact that sine squared plus cosine squared is equal to 1. All right, and we have some other corollaries such as the sum to product identities. The first one is cosine alpha cosine beta, where we want to single out on this term here, over here. And we can add this one here with the minus sine alpha sine beta to this one over here with the plus sine alpha sine beta. And with that, we end up getting that it's cosine of alpha plus beta plus cosine of alpha minus beta all over 2. And likewise, sine alpha sine beta is equal to, now we want to single out on this term here. So we can do this one here minus this one here, because then the cosine alpha cosine beta cancel out. And with that, we get cosine of alpha minus beta minus cosine of alpha plus beta all over 2. And finally, if we want to combine sine and cosine, then this is equal to sine of alpha minus beta, because that's where the sine formula comes in, plus sine of alpha plus beta all over 2. So all of these identities are very, very useful. And all of them stem from these main 2 identities. Focus all your efforts on memorizing only these 2. The other, I think, 7 identities, no, other 5 identities, directly come from this. So you only need to focus on memorizing this, or proving it with complex numbers if you want to. All right, so now that we've reviewed trig, we can now move on to equations involving pure lengths. So a question in geometry that we usually have to ask is, whenever we have a triangle ABC and we have 3 lines through the vertices, when exactly are these lines concurrent? Can we figure out a way to classify when they are concurrent? Well, let's suppose that the lines are concurrent to us beforehand, and we can figure out what must be true. So suppose that they have intersect a point P. Then we can use something called Ceva's theorem to prove that a particular length property holds when these 3 lines are concurrent. So what exactly is Ceva's theorem? Well, suppose that the opposite sides intersect each line at D, E, and F. Then Ceva's theorem states that BD over DC times CE over EA, so we're basically circling around the triangle, times AF over FB then, is equal to 1. And this holds when the 3 lines are concurrent. And note how this relation here is independent of the point P. The point P is not involved in this relation. And if we make all of these lengths directed such that BD over DC is negative if D lies outside of the segment BC and positive if D lies inside it, then this holds for all points P, not necessarily inside the triangle. Because, for example, if I have ABC here, and then the point P is here, suppose, then this is E, this is F, and this is D. And this statement still holds when we direct the lengths. All right, so how do we prove that the 3 lines being concurrent implies that we have that this quantity here is equal to 1? Well, there are 2 cases we have to consider. The first one is where P lies inside the triangle. In this case, the strategy is to use areas. And this may seem a bit out of the blue, but we have BD over DC is equal to the area of APB over the area of APC. And this is true because BD over DC is a ratio of the area of these 2 triangles here, but it's also the ratio of the areas between these 2 triangles as well. And therefore, if we subtract the area of the red triangle from the area of the blue triangle from the area of the red triangle, we get this yellow triangle here. And similarly, we get this yellow triangle here, which shows that BD over DC is a ratio of the areas of the yellow triangle. And we can similarly get that CE over EA is equal to the area of BPC over the area of APB. And finally, the AF over FB is equal to the area of APC over the area of BPC. And then we end up multiplying all these areas together in the end. And this area cancels out with that one. These guys cancel out. And finally, these cancel out. So the result is that their multiplication ends up being 1. All right, so that proves that when we have 3 lines that are concurrent, we get this relation here that holds. However, we already have a theorem for when 3 lines are concurrent, but we don't know how to prove that 3 lines are concurrent. So suppose we have these lines here. We don't know anything to prove that these 3 lines are concurrent. But we can try seeing if the theorem holds in reverse. So we have DE and F here. Then as it turns out, if BD over DC times CE over EA times AF over FB is equal to 1 in directed lengths, then this means that AD, BE, and CF are concurrent. They all meet at the same point. Okay, so how do we prove this? Well, this looks very similar to what we proved earlier, and indeed it is, because it's actually just the converse of it. So let's see if we can use this length relation when 3 lines are concurrent to our advantage. And this proof is really, really cool, so I highly suggest you pay attention to it. So let's suppose we get rid of this line here, and we have the point D sitting here. Then suppose that these BE and CF lines meet at point P, and we let line AP intersect the opposite side at D prime. So this is D, and this is D prime. Then we know that AD prime, BE, and CF are concurrent. So we wish to prove that D equals D prime. So note that we're using phantom points here. So we want to prove that these 2 points are the same. Now here's the cool part. We can use the Ceva's theorem for concurrency normally on the points D prime, E, and F because AD prime, BE, and CF are concurrent. Then we know that B D prime over D prime C times CE over EA times AF over FB is equal to 1 in directed lengths. And this is also equal to BD over DC times CE over EA times AF over FB. And these factors here cancel out, and so do these factors. So what we're left with is BD prime over D prime C is equal to BD over DC. And because this is true, this is actually enough to imply when we use directed lengths, this is why we use directed lengths, so that this implication becomes necessary. So this implies that D equals D prime. And exercise for you to practice directed lengths is to prove this. And with this, we have proven that D equals D prime, and therefore, because AD prime, BE, and CF are concurrent, this means that AD, BE, and CF are concurrent, as we needed. So here's an example problem that demonstrates how Ceva's theorem can be useful. So let ABC be a triangle, and let F and E be points on sides AB and AC of the triangle, and EF is parallel to BC. And if CF and BE intersect at a point X, we must show that AX bisects BC. In other words, AX passes through the midpoint of BC. All right, so the first step in any geometry problem, you already know it. Go ahead and do it yourself. All right. Assuming that you've drawn the diagram already, I'll go ahead and draw it now. So we have ABC, and then we have points E and F on the sides, such that EF is parallel to BC. and these lines here meet at a point x. And we must show that AX bisects BC. So suppose that AX meets this side at point D, so that we must show that these two lengths are equal. Well, what happens if these two lengths are equal? Well, if they were equal, then we can try using Ceva's theorem with this point x here on the opposite sides. So then BD over DC times CE over EA times AF over FB is equal to 1. And because BD over DC, we're going to be assuming that it's 1 and try working backwards. Working backwards is a very common tactic in geometry problems, and we can always reverse our steps. So we can get rid of this. So CE over EA times AF over FB is equal to 1. Or in other words, we have AF over FB is equal to AE over EC. So this looks very symmetric. In other words, the ratio of this to this is equal to the ratio of this to this. We want to show that this is like equivalent to EF being parallel to BC. And the reason why this is the case is actually just similar triangles. Because this is parallel to BC, we have these similar triangles AFE and ABC. And because of this, we end up getting AF over AB is equal to AE over AC, because that's just the ratio of the similitude. And therefore, this actually means that AF over FB equals AE over EC, or this holds. And this implies that D is the midpoint. We can be a bit more concise when we write our proof. And whenever you write proofs, as I said in earlier videos, you always have to write it forward. You have to not go backwards and to get something that's true. You always have to write it forward. So here's a way to write it. So we know that triangle AEF is similar to triangle ACB positively. And this means that AE over AC is equal to AF over AB. And this means that AE over EC is equal to AF over FB. And this implies that CE over EA times AF over FB is equal to 1. And by Ceva's theorem, we have, if this point is D, then BD over DC times CE over EA times AF over FB is equal to 1. So this implies that BD over DC equals 1, or BD equals DC. And this finishes the proof. All right, so now that we've done this example, we want to figure out how Ceva's theorem can apply whenever we don't have to intersect the other sides. Like, we want to find a version of Ceva's theorem that does not involve the other sides of the triangle. Like, it doesn't involve DE or F. So let's suppose that we have our triangle ABC again. And now we'll find a version of Ceva's theorem that highly relies on trigonometry. So we're going to be introducing the points D, E, and F again because they'll be useful in our proof. But really, the problem doesn't rely on it much. And we have these lines here again. Then the lines AD, BE, and CF are concurrent if and only if the following holds. So sine angle BAD over sine angle BAC times sine angle CEB over sine angle, or CBE, my bad, over sine angle EBA times sine angle AC F over sine angle FCB. And this is equal to 1. And the proof of this is to just use the ratio lemma on D. And by using the ratio lemma on D, we end up getting that BD over DC is equal to AB over AC times sine angle B80 over sine angle, this should be DAC. And similar relations hold for the other expressions. So if we multiply them all together, we end up getting BD over DC times CE over EA times AF over FB is equal to the sine product. So sine product times the extra factors in front. So AB over AC times then BC over AB times then BC over AC. And that's just equal to the sine product, since this term just disappears. So that means that the sine product is equal to 1 if and only if this product here is equal to 1. And this proves that AD, BE, and CF are concurrent if and only if this holds here. All right, so what's so special about this variant? After all, isn't it just equivalent to doing BD over DC and CE over EA and AF over FB? Well, yes, technically, but the beauty of it is that the points D, E, and F are not very involved, actually. Because if we erase these, then we could just replace it with a random point X, or we could let D be over here, and then E be over here, and F be over here. And this here still holds. All right, so with that said, let's move on to one final theorem before we go to our examples. Now, this last theorem is not particularly useful because we're going to be using Ceva's theorem most of the time, but you should know it just in case it comes up. And it's called Menelaus Theorem. And it states that if D, E, and F lie on the sides BC, AC, and AB, then D, E, and F all lie on the same line, they're collinear. If and only if BD over DC times CE over EA times AF over FB in directed lengths. Note the similarity with Ceva's theorem, but instead of being 1, this is equal to -1. And this is where directing lengths come in, because if we have a point B here, the point D is here, like D prime, then that means that if we draw these here, so D prime should actually be here approximately, then we have that B prime, BD prime over D prime C times CE over EA times AF over FB is equal to +1. So that's +1, and this gives -1. And that suggests a relation between the points D and D prime, something very inherently related. And this goes into projective geometry, and I'm not going to be discussing that in this course, but feel free to read up on it if you want to. So let's put all of our skills to the test by solving this problem. So let ABC be an acute triangle with circumcircle omega, and let the tangents to omega at points B and C intersect at point TA. And define TB and TC similarly. Show that the lines ATA, BTB, and CTC are concurrent. All right, so go ahead and try this problem on your own first. Go ahead and pause the video right now and try it on your own. And when you're done trying the problem on your own, go ahead and press play and we'll work on it together. All right, so I've assumed that you've tried the problem by now, so let's solve it together. So first we must construct a diagram. So we first draw a circumcircle omega, and we have A, B, and C is our triangle. Then the tangents to B and C to omega intersect at point TA, and similarly for TB and TC. So I'm going to be drawing it over here. So TB and that's TC. We want to prove that these lines are concurrent. All right, so we want to figure out what is so special about this line ATA. And if we want to prove that these three lines are concurrent, this naturally calls for a Ceva's theorem. But we don't have points on the side exactly. So because we don't have points on the sides, this calls for us using Trig Ceva. So our goal reduces to finding the sine of angle BATA over the sine of angle TAAC. So how can we do this? Well, we can try using law of sine chasing as earlier. So we want to somehow involve each of these angles. And the way we do this is by using law of sines on BATA and also law of sines on, let me move this up. So law of sines on TAAC. So what happens if we use law of sines on this first triangle? Well, then we end up getting that it's BTA over sine angle BATA is equal to ATA over sine angle ABTA, which is equal to AB over sine angle ATAB. And similarly, when we use it on this triangle here, we get TAC over the sine of angle TAAC is equal to ATA over sine angle ACTA, and this is equal to AC over sine angle ATAC. Okay, so now we know that this is true. We can involve both of these signs together, and we want the BATA to be on the numerator and this to be on the denominator. So let's divide equation 2 by equation 1. And when we do that, we get TAC over BTA times sine angle BATA over sine angle TAAC is equal to, then we want to somehow combine each of these guys. So which ones do we choose in this equation and this equation here? Well, we don't know anything about the angle ATAB. And we are only going to introduce AB over AC. So this is going to make it messier. So we're not going to be looking at that. So let's divide this one here by this one here. And when we do that, luckily the ATA cancels out. So what we're left with is sine angle ABTA over sine angle ACTA. And because TAC is equal to TAB, this is a property about tangents where the two lengths of the tangents are equal. So this factor cancels out. And what is left is that we have this relation here. Sine BATA over sine TAAC is equal to sine of angle ABTA over sine angle ACTA. Okay, so now we want to understand angle ABTA more. So what exactly is this angle? Well, we haven't really used the fact that BTA is tangent to the circle yet. In general, in geometry problems, we always want to figure out what we haven't used yet. And in this case, the only fact about TA being tangent to the TAB and TAC being tangent to the circle is that these two lengths are equal. That is what we used so far. So we want to somehow incorporate this tangent. And given this, we immediately know what to do with sine angle ABTA. Because angle ABTA inside an acute triangle like this, it ends up being 180 degrees minus angle BAC. Or actually, BC. Yeah, it should be BCA. And also, angle ACTA is equal to 180 degrees minus angle ABC. And this only holds when we have acute triangles. Inside obtuse triangles, it becomes different because then the directed angles are equal. But unfortunately, I don't really know of a way to combine directed angles with sine ratios. So we're going to be assuming that the triangle is acute for now. This is a rare case where using sines leads to configuration issues. Anyways, now using the fact that these are tangents, we end up getting sine of this expression here, and that gives sine angle BCA. Wait, hold on. So we get sine BCA over sine angle ABC. So therefore, what we ended up proving is that this is equal to sine angle C over sine angle B. And at this point, we can just repeat this to the TB and TC because that we can just apply the same logic. And doing so, we end up getting that sine angle CBTB over sine angle TBBA is equal to sine of angle A over sine angle C. And similarly, sine angle ACTC over sine angle TCCB is equal to sine angle C, or wait, this should be sine angle B over sine angle A. And therefore, when we multiply all of these three expressions together, we get that the product of these sine ratios here, which is equal to what we want by Cheva's theorem, is equal to the product of all of these guys here. But then the sine A terms cancel out, so do the sine B terms, and finally so do the sine C terms. So therefore, we have that the sine product is equal to 1. And this proves that we are done by Cheva's theorem. And therefore, the lines ATA, BTB, and CTC are concurrent. So the point of this problem is that using the law of sines in tandem with Cheva's theorem is often a very powerful technique for problems. So in the exercises, I'm going to include a bunch of examples that involve using the law of sines to your advantage. And I'm going to include a bit more examples that don't use the law of sines or Cheva's theorem. So it's kind of mixed practice in a way, but please do get comfortable with using the law of sines and performing manipulations like this. All right. Thank you so much for watching this video, and I'll see you guys in the next one.